Okay, welcome to section 5.3. We'll look at the Hilbert space L2. And we ended the last section with a reference to the fundamental theorem of infinite dimensional vector spaces, with a suggestion that with the right conditions, there's only one infinite dimensional vector space. Those right conditions are related to Hilbert spaces with certain extra properties. And it turns out those extra properties are satisfied by this space L2. So the space is rather fundamental in the theory of Hilbert spaces. It's fundamental in applications. Lots of applied math is done in the space L2. It turns out by the fundamental theorem of infinite dimensional vector spaces, every infinite dimensional vector space with certain properties satisfied will be isomorphic to L2. So this is quite a fundamental example of a Hilbert space. Take the interval AB to be a subset of the real numbers. Closed and bounded interval from A to B. We'll define the space L2 of AB as the set of all functions such that when we integrate the absolute value of that function squared over the interval AB, we get out a finite integral. Now, to deal with this in depth, we need to explore Lebesgue integrals, and these need to be Lebesgue integrals, not Riemann integrals. This is explored in great depth in the real analysis sequence that we have. A little bit more on that. The notes I use in fundamentals of functional analysis, in fact, these very notes we're looking at here are probably used as a supplement in that class more than anything in a standalone way. But in fundamentals of functional analysis, we look at the LP spaces. The online notes have a link to that. The detailed development of Lebesgue integration and Lebesgue the integrability of such functions is explored throughout the Royden and Fitzpatrick real analysis book. I prefer the 4th edition over some of the previous editions. Here we're talking about taking L2 over a closed and bounded interval. We can take the LP spaces over general measurable sets. So we needn't restrict ourselves to the interval A to B. We will in these notes, but that can be generalized. So some details will be missing here because we haven't explored Lebesgue integration and Lebesgue measure in any depth. But we can still discuss some of the more amusing properties of Hilbert spaces, in particular this space L2. Well, it's rumored to be a Hilbert space, so it must have an inner product on it, and the inner product must induce that norm. An inner product on L2 of AB is given by inner product of functions f and g is the integral over the interval from A to B of f times g. Assuming f and g are real valued, and we've been looking at some complex valued things, but notice if we take the inner product of f with itself, we'll get the inner product of f squared, and with the integral of f squared, and the integral of f squared is exactly what we have here. If we're dealing with real stuff, I don't really need those absolute values. I want to include them so we can talk about this in a setting where maybe we don't have real numbers everywhere. If f and g are complex valued functions of a real variable, then we define the inner product being the integral over a and b of f conjugate times f. So we need that conjugation. We'd want conjugate linearity in the first position, as we had in the previous section when we looked into inner products and introduced those for the first formal time. So if we had complex scalars and we had complex valued functions, then we could introduce an inner product, something like this, with a conjugation. Now, if we took the inner product of f with itself, we'd have the integral of f conjugate times f, which is the modulus squared of f. Again, in the complex setting, it would look exactly like this. So we're taking these integrable in the sense of having finite integrals, terminology from measure theory and Lebesgue integration. We're taking these collection of square integrable functions to form this space L2. The inner products, of course, induce a norm, the L2 norm. Inner products always induce a norm. These satisfy the properties of an inner product and so induce a norm. And so we're dealing with normed linear spaces. In addition, let me just authoritatively claim that these are complete inner product spaces. So they're Hilbert spaces. This is quite a claim, and we need to establish the completeness at some point for the LP spaces. But with that accepted, then these L2 spaces really are Hilbert spaces. And there's other Hilbert spaces. These L2 spaces are particularly nice Hilbert spaces. We'll see in the next section that, in some sense, all infinite dimensional Hilbert spaces are the same as L2. They're all isomorphic to L2. In some sense, it's not really all. It's all infinite dimensional Hilbert spaces with a few more details thrown in. Then we get spaces that are isomorphic to L2. And it's worth including these extra details because we end up with a space that behaves just like Rn. We can Gram-Schmidt process. We can represent linear transformations or linear operators, if you like. We can represent them as matrices. They'll be infinity by infinity matrices, but all that nice stuff from Rn carries over. We can have nice orthonormal bases for Hilbert spaces with a few extra details thrown in. Quick examples of Hilbert spaces other than capital L2 or the sequence spaces. Little L2 of R would be the set of all sequences of real numbers that are square summable. Little L2 of C would be the sequence of all, little typo there, all complex numbers that are also square summable. The sum from 1 to infinity, the modulus. So we should be taking moduli there, and that should be a complex number. I'll get that edited in the online notes. But in both cases, it's square summable in absolute value or modulus. And you know, that's a lot like what we had up here when we looked at the function space, capital L2. You're taking absolute values and you're summing. I mean, you're integrating. But aren't integrals just sums? No, they're limits of sums, though. Riemann integrals are limits of Riemann sums. Lebesgue integrals are, in a sense, they're limits of certain kinds of sums as well. It's a bit more of a long story there. But you certainly are used to drawing some sort of relationship between integrals and sums. They come out of sums. Integrals are limits of sums, Riemann sums in the Riemann setting. So the fact that we've had integrals of absolute value squared up there, and we got sums of, I could throw the absolute value in here, we're dealing with real numbers, sums of absolute values squared in this case, and blatantly in this case, the modulus is necessary because we need to talk real numbers in these bounds. Then there's certainly a parallel between the big L2 spaces and the little L2 spaces. In fact, little L2 as a Hilbert space with certain properties is isomorphic to capital L2. The neat thing here is, geez, to talk about this, I really need a number of details. The elements of this space are actually not functions. They're equivalence classes of functions that are equal almost everywhere. And then we get drug into the measure theory ideas of almost everywhere. These are much more tangible. This is kind of like Rn, except it goes on forever. Okay, well, it doesn't include all sequences of real numbers. The sequence 1, 1, 1, 1, 1, 1, 1, 1 of an infinite number of ones, that's not in that space because the corresponding series diverges. So what we've really done, it seems like, is kind of taken R infinity. I can treat R infinity, the sequence space. It's a linear space. Might have trouble putting a norm on it. I have to be clever about that. And I don't know about putting inner products on it. But it's kind of like we took R infinity, and under the usual idea of a norm, we threw out all the infinitely long vectors. And we'll talk about that in the future as well. And that will give us a very geometric interpretation of little L2 of R. This one can be dealt with without getting into all that stuff about measure theory because it just deals with sequences and convergence versus divergence of series. And that's just calculus too. So there's some quick comments about the L2 space. we'll really take those ideas and run with them in the next section and look at the fundamental theorem of infinite dimensional vector spaces. Terminology I made up, so you won't find it out there too much. Google those terms and probably just find my stuff that's posted online. But we'll elaborate on what I mean by that and what the in some sense ideas are and the added conditions that we'll need to put on these Hilbert spaces. It'll be awesome. It'll be worth a trip. We'll get all the geometry of Rn to carry over into these special Hilbert spaces. So have a nice day. I'll see you in section 5.4 shortly. And we'll look at that fundamental theorem and some other properties of Hilbert spaces.